All right, this is probably my favorite part of this whole section. The squeeze theorem is really fun. So let's introduce it a little bit. So you might remember this little limit. The limit as x approaches 0 of the sine in radians, although it's the same in degrees, of 1 over x. Remember, this limit doesn't exist. Sine of 1 over x just oscillates rapidly when you get really, really close to 0. And we saw this, looked at a function. So when it gets away from 0, it behaves pretty nicely. But really, really close to 0, it starts oscillating faster and faster, and it's not approaching anything. There's an infinite number of ones, there's an infinite number of negative ones. No matter how close we get to 0, this function just goes bananas. So this limit as x approaches 0 does not exist. But what about if we change it a little bit? What about the limit as x approaches 0 of x squared times sine of 1 over x? It's not changing it that much. What is this going to look like? Let's look at this new function. What happens if we multiply this by x squared? So it kind of looks like a line on either end, and then something's happening in the middle. Let's investigate. Let's zoom in a little bit. Or a lot of bit. So it's still oscillating a lot. It's still oscillating a lot, but it's much smaller now. Let's zoom in some more. Oh. So it's oscillating, but notice that the closer we get to 0, the smaller the oscillations become. So is there a limit? Kind of looks like there is, because it's getting smaller and smaller. Even though it's oscillating, it's still getting smaller and smaller and getting really, really close to 0. So we're going to introduce something called the squeeze theorem that essentially confirms this. And the way the squeeze theorem works is with two observations. Let's look at this other function. X squared. Let's make it pink. Notice that this pink graph is always above the blue graph. Even if we zoom in, right? The pink graph is always above the blue graph. Because sine is always between -1 and 1, right? Sine is never bigger than 1. So this pink graph is the biggest that the blue graph will ever be. You can see it. The blue graph eventually hits the pink graph. The pink graph is always at least the blue graph. Similarly, let's look at this orange graph, -x squared. Well, again, sine is always between +1 and -1, so the blue graph is trapped. The blue graph is trapped between orange and pink. Orange and pink are approaching 0. It's essentially trapped. It's essentially trapped by two things that are approaching 0. So it's stuck between two things that are approaching 0. It's getting squeezed into 0. That's what the squeeze theorem is talking about. Squeeze theorem, which we'll introduce shortly, says that if I have a function that behaves kind of wacky, but it's stuck between two other functions that I know how they behave, well, if they go to the same place, then the thing between them also has to go to the same place. All right? So let's introduce that a little bit. Let's look at the theorem, which again is going to be on that same document with all of these things that you don't have to memorize. So we're going to have 3 functions, just like we had. We did have 3 functions in this picture. Squeeze theorem says we have 3 functions, f, g, and h. Let's say that they're defined for everything. And again, it doesn't matter about the point itself. A itself doesn't matter. It can be defined at A. It can be undefined at A. When we look at limits, the function value at that point doesn't matter for the limit. So let's look at these functions and let's say, okay, they're defined everywhere close to A. In some open interval containing A means close to A. But what actually happens at A doesn't matter. So if G is between F and H, right? This just right means, this right here just means G is bigger than F and G is smaller than H. So if we look at some interval where this happens, it doesn't have to happen everywhere. But if we look at some interval around A, and this is happening, G is stuck between F and H. And if the limit of the left and the limit of the right go to the same number L. So again, let's wait on the conclusion real quick. So we have one function here. This is the biggest function, x squared. Another function. This is the smallest function, negative x squared. Blue is a function that's stuck between it. As we get close to 0, pink goes to 0. As we get close to 0, orange also goes to 0. So the big and the small are both approaching 0. So this is working for our little example. And as long as this limit is a real number, then the limit of this middle one is also equal to the limit of the other ones. All right, so the limit of the outside functions is going to be the same as the limit of the inside function. It is getting squished together. So let's use this in an example. All right. Example number 8. Apply the squeeze theorem. To find the limit as x approaches 0 of x squared times sine of 1 over x. So this is just asking about the limit that we're already talking about. So to use the squeeze theorem, you do have to confirm these things. And I'm not going to really make you confirm too much about function definitions, but this and this are the really, really big things that I am going to be asking you to do. Okay? Now, everyone say hi to October. So let's put all of this in the language of the squeeze theorem. We need an F and a G and an H. F is the little one, H is the big one, and G is the one in the middle, the one that we really are caring about. All right. We got some cat stuff going on right now. So this G is the middle. G is the one that we care about. This is going to be our G of X. And now in order to use the squeeze theorem, we have to have that G be squished between two things. So how do we find an F and a G that are on either side of this? We're going to go off to the side. No, don't chew my pen, October. No, this is not pen chewing time. We're going to go off to the side and say, okay, notice that sine of anything, it doesn't not matter what is on the inside of this sine. Sine of anything is always between -1 and 1. So if we multiply everything by x squared is always positive, so that's okay. Negative x squared is less than or equal to x squared times sine of 1 over x. It's always less than or equal to positive x squared. We have sandwiched this function g of x that we care about between two other functions. So we'll call this g of x, call this f of x, and we'll call this h of x. A lot of the times that we use the squeeze theorem is for trig. And for sine and cosine, you're always going to bound sine and cosine by 1 and -1. Okay? So we're going to say, so the red and the blue, that's like kind of our notes. And then this is, the white is like more of our proof. We're going to say, well, actually, it's all kind of included. So G is bounded by F and H. That's the first thing that we have to check, right? Is G stuck between F and H? And if it is, then we next look at the limits of the opposite sides. Right? The limit, right? F, right? What is F doing? As x approaches 0, this is a polynomial. So this approaches 0. This is a polynomial too. So H also is approaching 0. So G is getting squeezed, is what's happening. So that's our second thing that we have to check. We check the first thing, G is between F and H. Check the second thing, are the limits of those outside functions equal to each other? Well, the limit as x approaches 0 of the little function is equal to 0. And that's the same as the limit as x approaches 0 of the bigger function h. So we had to check this. We had to check this. So by the squeeze theorem, the limit as x approaches 0 of g of x is also equal to 0, just like we guessed from our little graph at the start of this video. So that's how you approach these ones. Bound the thing that you care about between two things that you know about that approach the same limit. And this is proof writing, really. So this logic is all part of our answer. I'm boxing our answer, but for points, this whole thing should really be boxed. All right. I'm gonna make a note to myself to do another squeeze theorem problem in the selected homework problems video here, because that logic and how you write your answer is very important mathematically. But we're not going to actually do a part B right now. But if you want to see another example of how to write this answer, then look at the next video. All right, so one more result that can be found with a kind of a complicated usage of the squeeze theorem. We're not going to get into where this comes from, but this is on your sheet as well. We'll use this a little bit throughout the section, and we'll prove it at the end of the quarter. The limit as x approaches 0, sine of x divided by x is equal to 1. This is on your sheet. This is something we're going to use throughout the quarter. We will not prove it until the end of the quarter. But it's related to the squeeze theorem. All right. So let's use it a little bit and do example 9. The limit as theta, again, limits are limits of functions. Functions can have any independent variable we want. The limit as theta approaches 0 of 1 minus cosine of theta divided by theta is what I want you to evaluate. So I guess technically this should say evaluate this. Well, direct substitution doesn't work here. Even if we assumed that cosine is continuous, which it is. We'll talk more about continuity in the next section. We can't plug in 0. Cosine of 0 is positive 1. So the top would be 0 and the bottom would be 0. Can't plug in 0. We're going to use some more tricks to evaluate limits. None of the tricks that we've talked about so far, a new trick, a trigonometric trick, trigonometric, never mind, a trig trick. We're going to say, okay, we have stuff with cosines. Jason just mentioned something about sines. Can we turn cosines into sines? Remember back to your trigonometry, your pre-calc 2. How do we get cosines to sines? And the short answer was we really couldn't unless we had a cosine squared. So we're going to go and get a cosine squared. So don't write this down. Why is this not okay? Why is this not helpful, rather? This would give us a cosine squared. but we'd have to distribute, and then we'd also have a cosine over here, so it wouldn't actually help us. What we're going to do, I said we weren't going to use another method that we talked about, but we are. We're going to multiply by the conjugate. If we multiply by 1 plus cosine of theta, we're still going to have a cosine in the bottom, but it's going to be okay because cosine of 0 is 1, so this is going to be a 2, and a 2 is nice. And this is going to fix our problem in the top. So we have, again, the difference of squares, and this is true as long as we're not dividing by 0. This is true as long as 1 plus cosine of theta is not equal to 0. But theta is approaching 0, so, right, cosine of 0 equals 1, so we're good on this. This thing over here is like really close to 2. So yeah, we're nowhere near that denominator being 0, so this is 100% okay. This is going to be the limit as theta approaches 0. Of the top, that's again that difference of squares formula. You can also FOIL this out if you wanted. It's going to be 1 minus cosine squared of theta. Oh, that should trigger something. Trigger a recollection. If not, that's okay. The denominator we're going to leave factored. Theta times 1 plus cosine of theta. Now that numerator, which may or may not look familiar, remember something. Pythagorean identity, sine squared of any angle plus a cosine squared of that angle is equal to 1. If we subtract a cosine squared from both sides, we get that sine squared of any angle is 1 minus cosine squared of that angle. So we can change cosine to sine in this way, as long as we have a squared. So this is exactly equal to sine squared over theta plus 1 plus cosine of theta. Now still, you might be saying, Jason, this is not looking any better. Why did we want sine? We wanted sine. I told you we wanted sine because I wanted to use this property at the top. And notice that we almost have that property. And we can get that property maybe with limit laws. When I say maybe with limit laws, look at this. This is going to be sine of theta divided by theta times the leftovers. This is what we want. What's the leftovers if we're going to write it like this? Well, we took out one sine of theta, so there's going to still be a sine of theta left. Sine times sine is sine squared. And on the denominator, we're left with a 1 plus cosine of theta. And we can split up these two limits as long as they both exist. Remember our limit laws. So the first one, we know that this limit is equal to 1 from that property that we can use. We're not going to prove this for a while. We're just going to use that property. So this first one exists. That's the first check mark required for a limit law, the product limit law. Does the second one exist? If we use direct substitution, if theta equals 0, the top is 0 and the bottom is 2. So both of these limits do exist and we can use limit laws. So this is equal to the limit as theta goes to 0, sine theta over theta, times the limit as theta goes to 0 of sine of theta over 1 plus cosine of theta. Again, this is the product law, since both exist. This first one is equal to 1 from that property. Second one is equal to 0 by direct substitution. And again, haven't explicitly proven why we can use direct substitution here. But it has to do with the fact that these trig functions are continuous. Sine and cosine are continuous everywhere. And so that could kind of pop up. But in the end, it is equal to 0. Let's look at this graphically. This is actually another very kind of famous law that we can prove at the end of the quarter. This is kind of where it's coming from. So let's look at y equals, this function is 1 minus cosine of theta, or x, divided by x. And sorry, I'm really zoomed in from before. Really zoomed in from before. There we go. This is what this function's actually doing. And it's not defined at 0, but you can see that it does get very close to 0 from both sides. All right, and that is one way of evaluating it. Using a result, this result can be gleaned from the squeeze theorem, but it's a little bit more of a complicated application. So let me know if you have any questions, and good luck.